So hi everyone, I'm Zhiyuan Wu from the Ballet School of Architecture at UCL. I'm a postgraduate student from the actual design under the research cluster 7. So I'm very delighted to present you the research project undertaken by myself and my postgraduate research team. So the Biotessera, a computational framework for machine learning guided biomaterial design. This presentation will outline our research motivations, methodology, and computational framework, explaining how we are trying to combine digital design with biomanufacturing. So before diving into the methodology, it's important to clarify the problem we are addressing. So in contemporary architecture, material systems are often treated as statics, predictable and replaceable. However, in a world shaped by climate uncertainty, users demand change frequently, and the technology accelerations. The statics notion of materiality becomes increasingly insufficient. So our project begins with fundamental questions, is that how can computational design engage with living, time-sensitive materials to enable architecture that learns and adapts over time? So to explore these questions, we first study the existing examples of material agent at different climates. As the angle was in Cambodia, that humidity and biological growth cause surface erosions, whereas the macropetru temperature variations and air dryness create cracking instead. So if we measure these erosions in digital perspective, we can find that in the first phase, visualized textures can be mapped into mass, void dataset, and then performing pixel-based agent detection through color differentiations. So this approach attempts to translate the material changes into quantifiable data inputs. So for these observations, two core questions emerges. How can we construct such biobuildings by controlling each stage of constructions, and how can we create a documentation systems to allow future applications for change? To examine these questions, we try to separate the traditional continuous architectures into the fragment coded pieces. So we revisited the mosaics traditions, the layering logic of architecture, and the regeneration capacity of biological materials to establish a computational framework for bioadaptive constructions. So these slides introduce the conceptual foundation of our framework, the tessera, or the modular fragment. So the tessera originating from the ancient mosaics practice, the tessera demonstrate how small and discrete elements can assemble into the complex patterns and meanings. So we reinterpret this logic into architecture from the declarative fragments to adaptive structural units. Here, we reinterpret the Stewart brand's concept of sharing layers as the idea that the different components of a building changes at different rates. So traditional systems rely on the fixed connections and the statics hierarchies influencing the permanent. So our biotessera process instead introduced interlocking and bioadaptive connections where each layer, the structure, the skin, and the surface is capable of aging, decaying, and regeneration independently. Extended this logic, we explored how the biological growth can redefine the maintenance from the passive repair to active regenerations. So we propose our four terminal strategies is the regrowing, reusing, regeneration, and redesigning, corresponding to different decades of transformations. So this process focuses on the fungal mycelium, transforming the tendon into active and continuous process throughout the building lifetime. So why are we using the mycelium? Because the mycelium embodies the philosophical principle. It sustains life through regeneration and fusing. To our perspective, the mycelium have the following three characteristics. The first one is that the mycelium undergoes a predictable biodegradation process from dense to porous, from inertial to eroded. This transformation lightens masses, reduce maintenance, maintenance, and reintroduce matters into the ecological cycles. So for architecture, it means end of life no longer equals demolition. The second one is that during the growth phase, the mycelium can grow together with wood structure to form composite structures. So this program growth enable modular assemble and reversal renewal, so allowing architecture to evolve dynamically while remaining low impact. So finally, the potential of mycelium lies in its global accessibility and reproductivity. So fungal species exist across diverse climates, enable local cultivation and digital fabrication. So given the sensitive of mycelium to environmental conditions, it's particularly important to first create a method that can be driven by the environmental factors. So by compiling the CFD-driven climate voxels with the site, we generate massing strategies and material allocations that are forecast-driven rather than from first. So this diagram summarizes the end-to-end workflow of our design. We begin with the voxel data input, the wind, the sun, and the urban context, then proceed to the massing generations, where the original massing is evaluated through the sun analyzed vertical creation and the area separations. The output inform material allocations. First, a voxel emerge harmonious in multiple fields. Second, allocation logic encodes rules for performance thresholds. And the last, space allocation distributes programs and material systems accordingly. This page demonstrates how to translate the CFD wind field data into the adjustable control ramps. So we read the wind speeds at each voxels and map them to a set of ramp functions, which modulates component densities, orientation, and scales. So on the left pictures, the safety data is injected into a point cloud within the site bounding box. So on the right, the distinct ramp logics generate different volumetric forms. So through these codings, we can precisely modulate the sensitive to wind exposure while maintaining the module's reproducibility. To strengthen the research, we conducted the monthly simulations. So the wind speed and directions curves drive voxel response from January to December, revealing how exposed hotspots and intensify. So this informs two design actions. First, zooming arrangements by exposure level to migrate the wind and rain impacts steadily, biomaterial matching to deploy porous or shielding structures to optimal shore locations. So these terminal resolutions enable early planning of maintenance cycles and material lifespans. So along with the wind field analysis, we also generate shadow voxels based on the multi-directional solar exposures. So average shadow depth drives vertical growth. So the deeper shadow accumulation controls the height, while the bright areas going upward expansions. So by analyzing exposure from the four directions, so we achieve a volumetric structures, optimizing daylight, pretension, and thermal control through the height, stepbacks, and the porosity. Next, if we have the data set of the environment, due to the relatively short lifespan of mycelium, a system capable of real-time monitoring the mycelium of agent is required. We are using the ULO and the CNN that we trained a detection model that identify and classify the agent conditions of myceliums across regions. So the samples So the samples are collected from London, Ankara, and Shanghai, representing diverse climates and environmental exposures. The workflow includes 3 stages: input, training, and result, leading to practical applications such as single blocks detections, composite samples, and full-scale digital reconstructions. And this page present foundation for the machine learning detections, the long-term observation of weather process of mycelium across varying climates. So over a three-month cycle, we recorded sample conditions every 1.5 months in the London, Ankara, and Shanghai. So observing changes across the dimensions including the volume, porosity, durability, weight, and color of mycelium. So results indicated that the London damp, cold climate accelerates the volume loss. Ankara's conditions cause the surface to cracking, while the Shanghai high humidity making the color a little bit different. So here we explained why we use the YOLO system. YOLO is original applied in the fields such as agriculture and medicine. So no one has trained the YOLO to detect biological materials. So our group intends to train it to detect the agent of biological materials within the buildings. So the part 1 detects erosion conditions by analyzing the RGB degradation maps. The part 2 identifies the colors and the surface. So up to now, the trained YOLO system has demonstrated the capability to detect cracks and erosions within mycelium bricks. Here are some slides visualize our training datasets and the annotation process. So the third and the final methodology is the biodigital fabrications, where the computational logic meets the biological growth. So this session introduced 2 hybrid connection systems, the bio-welding and the bio-bonding. So bio-welding focus on the mycelium to mycelium integrations. So 2 separated layers that are cultivated and fused after 1 week into a unified continuous part. Bio-bonding, on the other hand, it explores the mycelium to timber interface, forming composite components after approximately about 2 weeks. So to enable the biological precisions, we investigated the porosity control in mold designs. As you can see, this experiment compares the 2D poro patterns and the 3D oxygen diffusions models to evaluate how air circulations influence mycelium metabolism. The 3D acrylic mold shown on the right visualize the oxygen entry from the foresight, mapping the internal gradients that driven the fungal expansion. And this page demonstrates how voxel-based environment analysis can be applied to multiple designs. So we utilize environmental data to detect potential mycelium growth points, translating this into the variable poro densities. The result mode is calculated into 3 resolutions: the high, the medium, and the low. So each adapted to this distinct climate conditions is that the fine poros for the high wind or the rain zones, while the large poros serve sun exposure surface. And this integration of climate simulations data with manufacturing logic transforms the mode itself into a climate response bioinfiltration. Next, we present the oxygen control timber component fabrication. Through the digital curving, we generated diverse pores configurations that balance the weight reduction with oxygen. As illustrated, the prototype demonstrates how poro depths and spacing influence airflow and material densities. So by establishing the pore oxygen structure mapping, we achieve dynamic balance between the structural efficiency and the ecological responsiveness. So transforming the timber from a static building into a medium for expressive performance. So this page illustrates the manufacturing logic of acrylic molds. So before laser cutting, we processively calibrate the pore distribution across each surface to balance the oxygen exchange with carbon dioxide accumulations. Finally, the biowelding and the biobonding process brings the digital fabrication and the biological assembly together. Constructed from acrylic molds and timber framework, these prototypes enable controlled cultivations. The acrylic provides stabilities, while the timber introduces biological vitalities. So mycelium grow within and around the timber, bonding the two materials together. So the final section presents the results of our research, showing how the logic simulations, machine learning detection, and the biodigital fabrication combine together into ecologic systems. So we focus on both material level and architectural scale applications, demonstrating how the workflow operates from the micro growth to spatial assembly. So here we show the final results outputs of the YOLO-based detection models. So each sample was analyzed for erosion and the surface for erosion degradation. And these blue bonding boxes visualize detected aging zones with confidence scores, revealing how the systems distinguish different degrees of decays. And also this allows quantitative assessment of biological degradations, turning the natural agent into measurable data for maintenance and design feedback. So building on the trained model, we develop a simple real-time detection interface. The users can simply upload or capture image, and the system instantly identifies ages areas with confidence levels and the spatial annotations. So this interface translates a complex machine learning process into a simple tool for everyday monitoring. So bridging the scientific computation, with the architectural practice. So on the middle scales, we extend the monitoring system into a mapping system for building components. Through the voxel-based analysis, each component is embodied within the environment and structural data. The concrete distribution at the base is no longer fixed, but dynamically arranged according to the light, humidity, and airflow conditions, enable the structure to adapt environmental changes at the structural level. So this page demonstrates the integration of environmental data and the structural mapping. The left panel displays the structure loaded on the distribution diagram, while the right panel presents environmental factor, including the illumination, temperature, and humidity. So through this overlay analysis, each voxel simulation carries the dual structural and ecological information, providing precise guidance for subsequent material fabrication and allocation. And this page shows that the physical model we made and how it works. So this model integrates the mycelium, timber, and concrete into a layer systems, demonstrating that modular stacking and biointegration characteristics. The right detailed pictures show that the biostructure transition and textures at the material interface were active interactions between mycelium and concrete. So after 3 months, this model reveals visible biological transformations. The mycelium has darkened and wrinkled, while the concrete surface shows a minor infiltration patterns. So timber edges eroded slightly, produce softened boundaries between the materials. So, additionally, we applied our detection system to a wood mycelium composite models. So this result indicates that the aged regions were primarily concentrated at the material joints, specifically where humidity and biological activity were highest. So this experiment proves the system's capability to identify agent in the real materials. We also extend the detection framework to the digital design for the architectures. Simulated digital models visualize the agent process over the 3, 6, 12, and 24 months, with the system generated notions marking the zones of the predicted erosions. So this proves that the possibility of our workflow to transform the physical samples to digital environments, enabling the life cycle predictions and adaptive maintenance within the computational design systems. So thank you for your attention. If you have any questions further, please feel free to contact me with this email and our team members. Thank you.